Okay, my name is Brian Walker, experienced technical specialist in Unix databases, design delivery, architecture, project manager at HSBC. What I'll cover indexes, table types typically found in IBM DB2 and Postgres SQL, some references to Microsoft SQL, Oracle, and MongoDB. Examples are in Postgres syntax. What are indexes in databases? A data structure that improves the speed of data retrieval operations by creating a sorted list of values from one or more columns, along with pointers to original table rows. The sole purpose of indexes is performance, data retrieval. Indexes store separately from the table's main storage. Main storage required to store the index along with the original table. Indexes enable more efficient table joins. How indexes work? They are logarithmic math search complexity. This means that the search time is drastically reduced compared to linear search, something along a straight line. Complexity search. Don't ask me to explain the maths. Okay, who has heard of Ida Codd and Raymond Boyce? They invented the relational database model and the normalization. What is a key inside an index? A key is a column or a set of columns that uniquely identifies each row in a table, links the table together, and ensures data integrity, acting as a unique address for data to be found. A primary key is a column of columns in a database table with values that uniquely identify each row or record or does not contain null. A foreign key, these are fields in one table that link to the primary key of another table, establishing relationships between tables. A composite key, these consist of two or more columns in a table that uniquely identifies a row or record. A minimum super key, which uniquely identifies a row. A column or columns that an alternative key, a column of columns that uniquely identify a row. What does the concept of a natural key mean in a database? Hands up, do you know? A natural key typically has business value. For example, person's national insurance number, account number. Natural keys should be used to look up business value. Business value should mean to identify a user by email address for system XXX. Warning, natural keys can change over time due to business or external events, regulators, suppliers, which can complicate database maintenance, create performance problems, or history tracking. For natural keys to be useful, you should consider history tracking and that they stand the test of time. A killer natural is something uniquely identifies stock item, immigration visa number, a book number, that stands the test of time. Example supernatural keys, a VIN number, ISBN, and SQA, stock keeping unit number. What does the term surrogate key, does anyone know? Surrogate key has no business value. Typically auto-generated keys are most useful when performing join on data between relations, tables. Surrogate keys are well-defined database schemas that could use generated surrogate keys to identify all data held about an entity, stock item, person, for fast data retrieval. Surrogate keys make datasets more stable. Surrogate keys will always pass the test of time as they rarely change. A version key used to track version changes of row or base table and must be unique and not null, typically seen in data warehouse schemas. By understanding different keys in a relational database helps you pick appropriate columns or columns for index or filter in a select, update, delete statement. Helps you design your applications to exploit data correctly. Which is a better sortable data type or difficult to sort data type? Which is a better narrow columns or lots of columns in index? A sortable data type is always better for indexes. Int UID version 7, URD sortable data. They sort a sortable data type by embedding timestamps, making identifiers time ordered and roughly sequential. Char and var types, performance is the same, don't use floats. Difficult to sort data types, I've seen many examples, is UID 4. They're too random in nature, and it's caused fragmentation, increased writes, and low memory cache ratio. Query frequency. Frequencies, queries that will be used by an index. Range of queries sorting between result sets, write heavy, read heavy, write heavy workloads. Indexes a wide, simple index. Which is better, low cardinality or high cardinality in indexes time as a rule of thumb? Does anyone know? High cardinality. Your selected should be distinct rows by a total number of rows. It should be nearest as possible to 1. Let me explain in the next slide. For example, if you index and stored and reported and returned HTTP status codes for a RESTful API system, this problem will probably occur if you index on HTTP status codes column within an event table. There are only 603 regularly used HTTP status codes and a limited number of custom codes available. A few of these status codes, such as 200 successful, are most frequent. Index becomes top-heavy, difficult to cache, and never can be unique. Better solution with partition and created that, and return error codes such as generated surrogate key with the HSBC status code. Thus you could search the unique surrogate key for fast data retrieval to find more about the specific info warning. So here's an example, an index table, an HTTP table with a million records versus one with a surrogate key. You can see the time difference here. That's a panel, and then with a surrogate key. Does anyone know what a primary index in the table is? Anyone? A primary key. Primary keys are typically balanced tree indexes, and they look like this. If no natural, it's always better to have a primary key or use a surrogate key if you don't have one which is obvious. This could be used in scenarios with tools like IBM Q replication, Postgres logical replication. These tools use primary indexes to replicate data. If no primary index, then logical question tool will not work. And create a column-wide index that includes all columns or not work at all, not so efficient. So just some reminders. And some more reminders here. Right, onto unique indexes. Are unique indexes classified as a primary index? A unique index is always classified as a secondary index and never a primary index, as it could have null values. Example, searching a person based on line number. A lot of people don't have home landlines anymore, and land phone var char num is valid, common for these days. By allowing unique indexes to have null leads to unique indexes with nulls not distinct, unique index with nulls distinct, default, this is just beyond the scope of this presentation. What are secondary indexes? Typically unique or non-unique. A table can have many secondary indexes. A secondary index can have no columns. Secondary indexes allow for different column types, index types, Cluster indexes, DB2, MDC tables, ITC tables, dimension rates tables. Expression functional based indexes, partial indexes, DB2, Oracle, XML indexes. Second index types continue. Postgres GIST, SP GIST, text search based queries, GIN, another form of text indexes, BRIN, Postgres BRIN, block range indexes. Some secondary indexes in detail. A covering index, puts an index lookup and an index scan. So the objective is to actually include the data you're trying to retrieve an index, to put an index scan. Clustering indexes sorts and stores a table's data, rows of disk according to index key values, only one cluster index per table. A clustering can use primary keys or non-unique columns to a table. Some databases like MySQL only use a primary key as a clustering mechanism, so the term cluster index is more appropriate. A cluster index is also then a primary index. Cluster indexes, facts continued, excellent for range queries, examples, grouping data, comments, such as account ID in a transaction table with a primary key as a transaction ID. Partial index is a subset of table rows that satisfies a specific condition. Instead of indexing every row in a table, you define a where clause that determines which rows you get indexed. And partial indexes reduce index size, reduce index maintenance, overhead, and allow condition-based uniqueness. Partial indexes are especially powerful when you're only looking for 5 to 30% of the table row set. So that's an example of a partial index. Right, what database tools help you with indexes? Postgres Explain, DB2 Explain, Postgres Auto Explain, DB2 Advise, which tries to give you some indexes hints, Postgres Pure Stats, and Ops Manager, which is MongoDB. So we got negative effects of indexes. Too many indexes in a single table. Too many indexes on a single table continue. For example, if you had 6 indexes on a table, every insert into a table would result in inserts on the index record of those 6 indexes. Logically, 6 index pages will be updated, so effectively at least an overhead of 6 times. Low cardinality indexes, B3 indexes in particular. Some data engineers will not use them on purpose, no benefit, wasted disk space, wasted memory, wasted CPU time equals table scan. Indexes penalise database transactions. Index page must be in memory regardless whether any query uses them because they need to get updated by transactions. Effectively, the memory available to these pages get less. The more indexes, the more requirement for memory for effective caching. If you don't increase the availability of memory, this starts hurting the entire performance of the system. Random writes. Unlike inserts new tape records into table. Unlike inserts, new records into table rows are less likely to be amended into the same page. Indexes like B-trees are known to cause more random writes. Incorrect indexes. Indexes are never used by queries and waste disk space. Multiple column indexes where the first column is indexed on low county are not used. Indexes require maintenance, particularly clustering indexes and balanced tree indexes. More indexes, longer the maintenance. Recommendations for databases already built. Get a log of real queries, run on data on a typical day, add indexes so the most important queries hit the indexes in their execution plan. Use tools like Explain to prove index usage. Try to avoid indexing fields that have a lot of updates or insects. Try to avoid tunnel vision. Focus on the most single important select statement in the world syndrome. After a few indexes, get a new log and repeat. Has the situation improved? Recommendations on databases already built. If a situation has not improved, could I realise a table, use new features? Could I realise the table, use a feature unique to my database to solve a particular problem? MQ, clustering index, DB2, MDC table. Is database maintenance, lack of maintenance, an issue? Last but not least, sometimes it's best to be honest. Am I polishing a turd? Have everyone come across? But if you make that recommendation, make sure your line manager and the manager above knows about that. Recommendations for new databases, new applications. Ensure your schema is designed well, voice call and normal form. Use denormalized schemas wisely. As per the late Scott Hayes, if you module your data appropriately, you control your IBM licensing costs. Understand data retention. Is the policy archive deletes? How long, months, years? Why? Tables without data retention, bigger indexes. Can I use range partition, clustering indexes, block indexes to solve a particular problem? Prime benefit of range partition tables is partition elimination. If you can structure a table to use range partition tables correctly, your indexes on table could benefit. Recommendation for new databases and new applications. Continue. Understand history tracking, standard tested time. Columns use appropriate types, sortable types. Add indexes so the most important queries are indexed in the execution plan. Design application logic with a mindset of using indexes. Recommendations for new database continue. Design applications protect database sort transactions that was committed. Design applications to protect the data. Ensure when a user clicks run, submit, it's grayed out until the database transaction completes. I've seen too many databases die a horrible death due to repeat click, submit, root cause. Recommendations for new databases and continue. All types of tables have a primary key, so tools like Postgres replication can work now and in the future. Index columns with high cardinality first. Try to avoid index fields that lots of updates or inserts. Define separate maintenance windows for backup table index maintenance. Upgrades to store automation features, auto vacuum. Recommendations for new databases, new applications, continue. Ensure that UAT has similar database architecture and database size. For example, a logical DB2 DPF data partitioning database behavior is totally different to physical DB2 DPF. Have a look up the term broadcast joins. By having similar size databases, you can use explain to satisfy, describe your query, and be common indexes will be used in production. If your database supports hash sharding partition, ensure your distribution key promotes co-located joins, and your indexes use the distribution keys to locate data. An index that uses distribution key will benefit the horizontal parallel processing. That's MongoDB Shardit or DB2 DPF. Make sure you've got database mentions, particularly Postgres, auto vacuum, regular target manual vacuuming of large tables, regular Linux checks. DB2, this could mean reorgs, run stats, auto run stats. Understand bulk DBO operations, such as mass updates, deletes in the data. This time your maintenance on operations after the bulk operations. Right. As a data table require maintenance, never assume. Postgres, auto vacuum, there's an extension called PG bloat check, manual vacuum, PG repack, PG squeeze. Remember, auto vacuum will not address index or table bloat. Right, summary. Don't use more than 5 indexes per table for LATP. In a data warehouse schema, several indexes bigger than its table fine. It's not so fine in LATP database. Ensure all indexes are used for the table. Delete indexes that are not used. Use appropriate column types. Type is sortable. Index on high cardinal columns first as a rule of thumb. Understand the sequential random nature of data to see if clustering is useful. That's it, and that's my LinkedIn profile. Thank you.